Hello everyone, welcome back to Synthesis Workshop. My name is Aidan Luby, and I'm one of the editorial board members here on the channel. Today's episode, we will be joined by Dr. Georgia Harris, who recently completed her PhD in organic chemistry at the University of Cambridge as a part of Professor Matthew Gaunt's research group. Georgia is now a postdoctoral researcher at the University of Manchester, working with Professor Nicholas Turner. Today, we will continue our synthesis module of Synthesis Workshop's Advanced Organic course, and we'll be looking at an introduction to radical chemistry, a concept that I will now be turning over to Georgia. Thank you again for joining us on the podcast.
Hello, my name's Georgia, and I'm a final year PhD student at the University of Cambridge. And today I'm going to give you an introduction to radical chemistry, a topic that has been central to my research in the field of photoredox catalysis. Radicals are incredibly important reactive intermediates, appearing in biological pathways as well as atmospheric processes. However, their application within synthetic chemistry has often been limited, in part due to the assumption that their high reactivity corresponds with low levels of reaction selectivity. Today, though, I hope I can show you that this is not the case and display that radicals are in fact incredibly important intermediates within modern synthetic chemistry. In today's episode, we will mainly focus on traditional synthetic radical chemistry. We will first look at structure and stability, investigating radicals from an orbital perspective. We will then go on to look at radical reactivity modes, which can be typically classed into four main categories. We will then move to look at radical selectivity, considering the different factors that control how radicals react with other species. Finally, we'll go on to look at radical generation modes, looking at the different ways radicals can be made from apparently stable molecules. Throughout this episode, I'm also going to try and highlight modern radical chemistry examples from the recent literature, in particular looking at the areas such as photoredox catalysis and electrochemistry. First of all, it's important to consider what we mean by radical. A radical is a reactive intermediate that possesses an unpaired electron, and as you can see, in contrast to polar species, the movement of this single electron can be represented by a single-headed curly arrow, in contrast to the normal double-headed curly arrow we're used to seeing. When we consider the stabilisation of polar intermediates, we know that anionic intermediates are typically stabilised by adjacent electron withdrawing groups, whilst cationic intermediates are stabilised by electron donating groups. However, when we consider unpaired radical species, these can be stabilised by both electron donating and electron withdrawing groups. Looking first at the molecular orbital diagram on the left, in the case of an adjacent electron donating lone pair, whilst the energy for the newly formed singly occupied molecular orbital, or SOMO, is raised compared to the atomic orbital, the stabilisation of the newly doubly occupied molecular orbital is large enough to lower the energy of the overall system. In the case of an electron withdrawing system, mixing of the pi star and the radical orbital can allow the formation of a lower energy SOMO to stabilise the radical. In the examples we have looked at, we have considered how radicals can be stabilised by either an electron donating group or an electron withdrawing group. However, in some examples, radicals can be stabilised by both of these types of groups simultaneously, in what is known as the captative effect. The combined stabilisation of these groups is greater than the additive stabilisation of the groups individually, and the resultant push-pull radicals underpin many important biochemical pathways. On the screen, you can see an interesting example of this with ascorbic acid, or vitamin C, which acts as a radical scavenger in the body, reacting with harmful species such as hydroxyl radicals to form a stable captative radical, acting as an antioxidant. The type of stabilisation we have discussed so far is thermodynamic stability, and can be invoked through interactions with neighbouring groups. However, radicals can also be kinetically stable through steric restraints, and these are known as persistent radicals. On the screen you can see one example of this in TEMPO. This is stable under ambient conditions, with dimerization prevented due to the flanking tetramethyl groups. The bright red colour you can see is caused by the unpaired electron, allowing the molecule to absorb in the visible region. It is a useful reagent in many oxidative reactions, as well as being a mechanistic probe for radical processes. The stability of this radical also makes it possible to visualise the unpaired electron using electroparamagnetic resonance spectroscopy. This technique is analogous to NMR, but it exploits electron spin rather than nuclei spin. The observed geometry of radicals is closely related to the stabilization of radicals through orbital hybridization. And as you can see from the scheme on the slide, as p character increases for the radical containing orbital, so does the stabilization. This can be rationalized by considering the stabilizing factors for these orbitals. For example, in the leftmost example, the sp2 orbital is perpendicular to the aromatic system, meaning it cannot be stabilized by the pi electrons. However, looking at the rightmost example, and the p orbital containing the radical, this conceivably could be stabilized through hyperconjugation to neighbouring bonds. From this trend, it would be reasonable to expect that all alkyl radicals adopt a planar conformation. And indeed, for the methyl radical, this is the case. However, as the electronic and steric nature of the radical substituents are varied from hydrogens, this can change. Taking the trifluoromethyl radical on the screen as an example, we can see that this adopts an almost pyramidal structure. And this is due to in-phase interactions between the SOMO and the LUMO, forming a new lower energy SOMO, resulting in radical stabilization. This favourable interaction can occur due to the increasing sigma acceptance of the fluorine atoms in comparison to the hydrogens, which results in a lowering of the LUMO energy. At the same time, the pi donation of the lone pairs on the fluorine raises the energy of the SOMO. These two effects work together to lower the energy gap between the LUMO and the SOMO, allowing the orbitals to overlap more efficiently, resulting in greater radical stabilization and a greater deviation in radical geometry away from planarity. If instead of fluorine, the hydrogens of the methyl radical were substituted for a pi accepting group, this would lower the SOMO energy, resulting in an increased LUMO-SOMO gap, and this would favour a planar structure in the radical geometry. Now that we have looked at radical structure and stability, we are going to move on to consider the ways in which radicals can react, and there are generally considered to be four main reaction modes. The first of which is addition, whereby a radical adds into an unsaturated radical acceptor. This is a particularly important class of reactions when considering the formation of carbon-carbon bonds. The second reactivity mode is abstraction, or substitution, and in contrast to polar processes, this typically occurs at a monovalent atomic centre, depicted here as X, rather than at a carbon centre. The third reactivity mode is recombination, whereby two radical species come together to form an electron-paired species. The final form of reactivity is elimination, where a radical species fragments, liberating a molecule, typically a gas such as nitrogen or CO2, and generates another radical species. We will look at examples of each of these reactivity modes throughout the presentation. However, first it's important to consider the selectivity of these reaction processes. Radical selectivity is usually dictated by several factors: the philicity of the radical and other reagents, the relative bond strengths of the bonds being made and broken, as well as steric effects. Bond dissociation energies are a helpful measure of radical stability and a useful tool when it comes to predicting reaction outcomes. On the screen, you can see a scale of carbon-hydrogen bond dissociation energies. And in general, the lower the bond dissociation energy, the more stable the resultant radical. Many processes rely on this thermodynamic driving force towards stability to generate their desired products. And looking at this scheme, the trend in bond dissociation energies correlates well with the factors that we've already considered that are known to affect radical stability. For example, on the left-hand side, sp2 hybridized orbitals are generally less stable than the sp3 orbitals, whilst electron donation, withdrawal, and conjugation all stabilize the unpaired electrons. In terms of radical philicity, radicals can display both nucleophilic and electrophilic characteristics, depending on the surrounding electronic structure. For example, carbon-centered radicals adjacent to a heteroatom, such as oxygen or nitrogen, are stabilized by the partial donation of the heteroatom lone pair to the SOMO, giving the radical nucleophilic character. A similar effect is also observed in alkyl radicals due to hyperconjugation. On the other hand, carbon-centered radicals adjacent to a pi acceptor can donate their unpaired electron into the pi star orbital, making them electron deficient and therefore electrophilic. sp2-based radicals, such as aryl radicals, typically sit somewhere in between and are described as ambiphilic. Now moving away from carbon-centered radicals and instead considering the philicity of heteroatom-centered radicals, you can see on the screen a trend in electronegativity across a series of elements. The elements on the left, shown in blue, are less electronegative than carbon, and therefore display nucleophilic characteristics. However, the elements shown in red on the right-hand side of the screen are more electronegative than carbon and therefore display electrophilic characteristics. An understanding of bond dissociation energies and radical philicity, as we've discussed, can be helpful when predicting and rationalising the selectivity of radical reactions. This is particularly important in the context of complex molecular systems for controlling chemo and regioselectivity. In Riesman's 2018 synthesis of pleuromutilin, 2 successive radical reactions were employed in the construction of the natural product. The first being an addition reaction, whereby an alpha-oxy radical adds across an alkene. In this example, there are 3 carbon-carbon double bonds in the intermediate in question, leading to 6 possible ways the radical could add into them. Considering the philicity of the alpha-oxy radical, which we now know to be nucleophilic, explains the observed selectivity for addition into the electron-deficient enone at the beta position. The second radical step, shown on the right of the screen, was an intramolecular hydrogen atom abstraction, or a substitution reaction. And through a comparison of bond dissociation energies, we can see that the resultant alpha-oxy radical formed is more stable than the initial alkyl radical. In some cases, a reaction may be slow due to a mismatch in radical philicity. In this case, a process called polarity reversal catalysis can be employed in order to drive the desired transformation. This technique is exemplified in an example from Guvner and Willis at the University of Oxford in collaboration with Janssen. This transformation is a formal hydrosulfonation process and involves the addition of a sulfur-centered radical into an alkene. Addition of the radical into an electron-deficient alkene results in the formation of an electrophilic radical, which is well disposed to undergo a hydrogen atom transfer process with the hydridic hydrogen of a silane. On the other hand, if a radical adds into an electron-rich alkene, a nucleophilic radical is formed, and this cannot undergo a polarity-matched hydrogen atom transfer with silane. Instead, a catalytic amount of a thiol can be incorporated, allowing a polarity-matched hat between the nucleophilic radical and the protic hydrogen of the thiol. The thiol is regenerated by the sulfur-centered radical undergoing hydrogen atom transfer with the silane present in the reaction mixture. Therefore, via this polarity reversal catalysis process, the hydrosulfonation of both electron-deficient and electron-rich alkenes has been demonstrated. We have considered the stability, geometry, and selectivity of radicals, but now it's time to look at how these species are actually formed. Whilst there are lots of different reagents and reactivity modes that enable radical generation from spin-paired molecules, they all typically fall into one of 2 categories, either bond homolysis or electron transfer. The unpairing of a bonding pair of electrons by homolysis underpins the chemistry of traditional radical initiators, and can be triggered by heat, light, or energy transfer by sensitization. In the case of peroxides shown on the screen, the weak oxygen-oxygen bond can be homolyzed directly to form 2 oxygen-centered radicals. Another important radical initiator, pictured below, is azo-bis isobutanitrile, commonly referred to as AIBN. This too can decompose under heating or irradiation, driven by the release of molecular nitrogen and the generation of stabilized tertiary radicals. Both of these initiators can be drawn with a single pair of fishhook arrows as shown. However, it is worth noting the different ways in which the mechanisms of these radical reactions can be drawn. So, in figure 1 at the bottom, you can see, as we've depicted above, the single pair of fishhook arrows coming together to show the forming of the nitrogen triple bond. However, what is not depicted is the pair of electrons moving in the other direction away from the homolyzing bond. This can be shown completely in figure 2. Alternatively, you can also draw arrows as shown in figure 3, where the opposite pairs of moving electrons are depicted. All 3 depictions are equally valid and mean the same chemical process is taking place. The radical initiators that we have just discussed can be used to start radical chain processes, such as the halogenation of alkenes. In this example, dibenzyl peroxide can be used to generate an O-centered radical following homolysis. This can then abstract a hydrogen from hydroboric acid to generate a bromine radical. As we've already discussed, bromine-centered radicals are electrophilic and therefore are well matched to undergo addition into an electron-rich alkene. Following radical addition, the resultant alkyl radical can undergo hydrogen atom transfer with another equivalent of hydroboric acid, regenerating the bromine radical and propagating the chain process. It is worth noting that this radical process proceeds with opposite selectivity to the polar Markovnikov bromination of alkenes, highlighting the complementarity of radical reaction manifolds to traditional polar processes. Finally, termination of the radical process can occur by the recombination of radicals to generate electron-paired species. A particularly important class of radical chain reactions is free radical polymerization. This process is dominated by the propagation step, where addition of a radical into successive monomers enables the growth of the polymer chain. More recently, radical processes which can break down polymers into useful commodity chemicals has become an area of particular interest, due to its application in the recycling of plastics. In this recent example from the Reisner group, it has been demonstrated that the photocatalyzed hydrogen atom abstraction, followed by oxidation and fragmentation, can allow the conversion of polystyrene to benzoic acid. Like dibenzyl peroxide, AIBN can also be used as an initiator in many analogous transformations, but can also be used to homolyze tributyl tin hydride, forming a nucleophilic tin-centered radical which can be used for functional group removal. The dehalogenation of alkanes is one of the classical modes of reactivity of the tributyl tin radical via the direct abstraction of a halogen atom. The resultant alkyl radical can then abstract a hydrogen from another equivalent of tributyl tin hydride, propagating the radical process. More recently, the field of photoredox catalysis has emerged as a powerful way of generating radicals under mild, visible light-mediated reaction conditions. In 2020, Leonori reported a photocatalytic manifold for halogen atom transfer, this time using photochemically generated nucleophilic alpha-amino radicals for halogen abstraction. This allowed the use of triethylamine in place of the toxic tin reagent as a radical precursor. In a final example of using tributyl tin radicals for the removal of functional groups, we're going to look at the Barton-McCombie reaction. This process is used to deoxygenate alcohols. The free alcohol is first converted into a thiocarbonyl derivative, which is subsequently attacked by a tin-centered radical, driven by the formation of a stable tin-sulfur bond. Fragmentation generates an alkyl radical, which can then abstract a hydrogen atom from tributyl tin hydride to form the deoxygenated product. In contrast to bond homolysis, radicals can also be generated by the direct addition or removal of an electron from a spin-paired molecule, in a single electron reduction or oxidation event. Certain metals, such as sodium and magnesium, can be used in dissolving metal reductions. In these reactions, a metal is dissolved, liberating free solvated electrons, which can then interact with organic molecules also in solution. The Birch reduction is a prominent example of a dissolving metal reduction, commonly using sodium in liquid ammonia for the reduction of aromatic rings to dienes. Regioselectivity in this reaction is dictated by the electronics of the ring and their ability to stabilise the anionic radical intermediates. You can see on the screen, the image on the right-hand side shows the dark blue Birch reduction taking place, the blue colour resulting from the electrons in solution. Another well-known dissolving metal transformation is the pinnacle coupling, which unites two carbonyls to form diols. This is usually a homocoupling reaction, although it can also be employed intramolecularly in heterocoupling ring closures. Mechanistically, it involves the single electron reduction of both carbonyls to form alpha oxy radicals, which then can recombine to form a carbon-carbon bond. Since its discovery in 1859, there have been many variations developed, with more recent takes on this process using alternative methods to mediate the reduction. For example, in 2019, this electrochemical metal-free pinnacle coupling was reported, using a boron-doped diamond electrode for the homocoupling of aryl ketones. Moving away from dissolving metals, inorganic compounds such as samarium iodide can also be used as single electron reductants in organic processes. Samarium iodide is capable of reducing a variety of functional groups, but it is most commonly employed in the reduction of carbonyls. In this 2023 paper from Proctor, samarium iodide is used for the reduction of ketones. The resultant alpha oxy radical can then rearrange to open the adjacent bicyclobutane and reacts with an alkene in an addition reaction before recyclizing to form a bicyclohexane. In this process, the ketone is reformed, meaning that samarium iodide is only required in catalytic amounts for this net redox neutral process. Inorganic single electron oxidants like samarium ammonium nitrate, or CAN, are also widely used in organic synthesis. In this example, CAN is used to oxidize a sinyl-enol ether, which following fragmentation leads to the generation of a radical adjacent to the newly formed carbonyl. This is particularly interesting as it highlights a common feature and advantage of radical chemistry, as what was a nucleophilic carbon in the sinyl-enol ether has become electrophilic in the radical species, reversing the selectivity in an Umpalung effect. Bringing together everything that we have covered today, we're now going to explore radical cascade processes, where a sequence of well-defined radical steps can be triggered in a single reaction. This highlights the utility of radicals in complex chemical settings, dispelling the idea that radicals are too reactive to be used selectively. In the example shown here, an oxidatively triggered radical cascade is used to assemble the core structure of limonene in Yamashita's 2015 total synthesis. This cascade consists of 3 addition reactions, and specifically in this case, radical cyclizations, to assemble the 3 rings. The ring closures follow Baldwin's rules, which are equally applicable to radical cyclizations as they are polar processes. In addition, the cyclization's regioselectivity can be rationalised using Beckwith's rules, which are later additions specific to radical cyclizations. The 2 6-endo-trig cyclizations result from the desire for the radical addition to occur at the less hindered end of an alkene, and the 5-exo-dig can be explained by the kinetics of the cyclization. In addition to ring closure, radicals can also trigger ring opening in certain contexts. We have already seen this, for example, in Proctor's radical synthesis of bicyclohexanes via the opening of bicyclobutanes. Ring opening tends to be restricted to highly strained systems, so the most common example is the opening of cyclopropane. This system has been very well studied and can be used in kinetic studies as a radical clock or embedded in substrates as a mechanistic probe. Finally, whilst I don't have time to do justice to these topics today, scattered through this episode have been examples of photo and electrochemical processes for radical generation, which have become increasingly important in the context of organic synthesis over the last few decades. These technologies allow us to take a huge variety of functionality and generate radicals under exceptionally mild conditions. They also display excellent functional group tolerance and have the potential to create a much more sustainable way of carrying out radical transformations. Photoredox catalysis uses visible light accompanied with a catalyst that can absorb in the visible region to mediate the single electron transfer processes. Electrochemistry, on the other hand, uses the application of a voltage to perform oxidations and reductions. It can be carried out on a very small scale in benchtop setups in research labs, shown on the right, as well as being scaled well to perform on process, shown in the middle. If you want to find out more about these topics, keep an eye out for future videos from Synthesis Workshop, which will cover them in more detail. So in summary, today we have discussed what a radical is and how they can be generated for use in organic synthesis. We have looked at the ways in which they can be stabilised and how this can affect their geometry, reactivity and selectivity through considerations of orbital interactions, bond dissociation energies and felicity. There are 4 main types of reactions a radical engage in: addition, substitution, recombination and elimination, and we have looked at examples of all of these. I hope I have also been able to demonstrate the applicability of radical transformations in complex molecules and complex reactivity modes. Finally, we have touched on the growing importance of photoredox catalysis and electrochemistry within the context of radical chemistry and the great additions they make to the synthetic chemist's toolbox. I really hope you've enjoyed today's episode. Thanks very much for listening.
Thank you, Georgia, for an excellent talk. Understanding the characteristics of radicals makes them a valuable synthon for natural product synthesis, but also plays an important role in photoredox catalysis, electrochemistry, even depolymerization of polystyrenes, and much more. We would like to thank you for joining us in our Introduction to Radicals video as a part of our Advanced Organic course. And be sure to leave a like and subscribe to the channel if you enjoy this content, and leave a comment of your favorite utility or application of radicals in chemistry. See you next time.